Hi, in this video I'll explain the working of the Archimedes principle, which is also derivable from Newton's laws of motion, as it just balances the forces as you do in a free body diagram. So here you see a ball that's floating in water. It's just suspended and it is in equilibrium. 3/4 of the ball is under the water line, which you can see as a blue line, and the hydrostatic forces are acting on the submerged portion of the ball. Obviously, the hydrostatic forces will not act on that portion of the ball which is above the water. So now the vertical force is the weight that's pointing downwards, and the Archimedes principle talks about the force of buoyancy that acts upwards to keep things floating. The upward buoyancy force is a function of the weight of water that the ball displaces. So first we have to find out how much of volume of water the ball has displaced, the submerged portion of the sphere, and then what's the weight of that volume. So let's look at an example. I've just put in a plastic dish into water. It's floating. Most of the dish is above the water, which shows that it's a very comfortable case of flotation. The weight of the plastic dish is so low that it has to displace a very small amount of water, and that volume of water that the dish has displaced, the weight of that volume is sufficient to keep the boat floating, both for the yellow dish and for the green bowl that's in that video. The green bowl is so wide and shallow that it has to displace only a small amount of water. Now let's take a case of a stainless steel bowl. Stainless steel is of course much more denser than water. And how does that float on water? So again, it's shaped like a bowl, so it's displacing a volume of water, and the weight of that displaced volume of water is acting upwards and balancing the downward force due to the weight of the stainless steel bowl. And you can see the water line, it's about 1/5 of the height of that bowl. Now what we will do is we will put more weight into this. Most ships are made of steel, not of wood nowadays, so let's put some weight. As we put some weight, the whole stainless steel vessel has sunk deeper into the water. The water line has come up to half of its height. It's still floating, which means that this shape is good and it is sufficient to displace a volume of water, and the weight of that volume of water is sufficient to balance the weight of the stainless steel dish on dish. So that was interesting. And now let's look at a numerical problem. So we have a ball